So, today we will talk about Faraday's law of induction. All of you know that famous experiment you must have done in school days. You take a coil and connect it to a galvanometer, then take a magnet, move the magnet through the coil and you see galvanometer deflecting, or keep the magnet fixed and move the coil near it and again you see that galvanometer deflects. And this phenomena of generating electricity to deflect the galvanometer by movement of coil or magnet is responsible for all power generation in different power plants. The electricity that we get in our houses or industries comes from such magnet coil movement only. So, we will start with repeating this experiment on our table and then we will discuss the physics of it, why it does and how it does. So, you can see the instrument, we have this galvanometer and this is in fact a coil. This blue thing that you are seeing is just a tape. We have put a coil, several hundred turns, and then it is fixed with the help of this tape. And this cart is to facilitate the movement of this coil. The galvanometer is connected to this coil. So, this is the simplest variety of circuit you can think of. And then I have a magnet. This is our magnet, cylindrical magnet. There are 3 of them just to make it more stronger. This is an iron rod. I am using it as a stand to hold it, a handle. This is like a handle. So, repeating Faraday's experiment, I am moving this magnet close to this coil. In fact, I will take it inside this empty space and you look at the galvanometer. Can you see? When I take it in, there is a deflection. When I take it out, there is another deflection in opposite direction. And the other part, keep the magnet at its own place, fixed at rest, and move the coil. So, this is it. So, you have current. The galvanometer deflects because you have current, and the current is generated without battery, without using power supply, without using these power outlets in the sockets. So, it is only movement either of the coil or of the magnet. This relative movement between coil and magnet produces this electricity, very famous thing. But now let us understand physics of it. First, let us understand the part where the coil is moving and the magnet is fixed. It is like this. Here is the magnet and then the coil is moving and a current is generated. Now, current generated means what? You have the wires, the turns are going like that. So, the free electrons have started moving along the length of the wire. So, either this way or this way, depending on the direction of the current. So, why these conduction electrons have started moving? What pushes them in a particular direction so that there is a definite current? So, we can again go back to our famous equation F equal to QV cross B. Force is charge, then velocity and cross product with the magnetic field. So, if the magnet is here, what kind of magnetic field exists at the site of the coil? Now, the magnetic field of a magnet, you must have seen this kind of figure, is of this kind. The field of a magnet, permanent magnet, cylindrical magnet, is of this kind, it's like this, diverges from that surface, flat surface which you call pole. So, the field is at different places, at different points, fields have different directions and different magnitudes, it diverges from the face. So, what kind of field will be here at this point? So, what I do is, let me remove some of the field lines and make them, some of them I will retain. Okay. So, let us focus on these 3-4 lines which are diverging, and okay. So, let us focus on these lines, okay, on these lines, and let us say my magnet is here, and this these are the field lines, and a particular field line which passes through this point of the coil somewhere here, what will be its direction? What is the suggestion by these field lines? The magnetic field is going like this. So, this is the direction of the magnetic field. And what is the direction of velocity? When I am moving the coil, what is the direction of velocity? So, that velocity direction, if I point, suppose it is going like this. So, this is the velocity direction. So, this white chalk, this gives me kind of direction of velocity, is going like this or going like this. So, think of these free electrons at a certain point on this coil. Consider any turn and you have free electrons there, and when I am moving the coil, that turn is also moving and the electron is also moving, and the velocity is along this white chalk, and the magnetic field which exists because of the magnet that I had put, that is in this direction. So, what is Q V cross B? So, V cross B. So, here is V horizontal and here is B, and if you do this V cross B, look at the direction of V cross B, it will be along the turn, this way or that way, it will be along the turn, and therefore, the electrons are driven along the turn, and that happens everywhere. I have taken a point at the top, you can take the point anywhere, here, 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 here. There is cylindrical symmetry, the field lines just diverge like that. So, you have cylindrical symmetry. So, you can take the point here, you can take the point here, you can take the point here, everywhere Q V cross B will be in the same sense. So, it will drive a current and the galvanometer will deflect. So, that is the mechanism. So, here is another experiment, beautiful experiment. In this experiment, I have two solenoids, one is here, another is here, and they are connected through these wires. Then we have a magnet here, and this magnet is hanging from this spring. I have another magnet in my hand, and that is the setup. Now, let me try to bring this one at rest. All right, roughly. And now I take this another magnet and move it in and out here. And you look at this spring here and see how it starts oscillating when I move this magnet. Okay. So, I am moving magnet in solenoid number 2, and the magnet in this solenoid number 1 is oscillating together, and if I stop, this also damps out, this oscillation also damps out. I do it again, Yes. So, my movement of magnet in this particular solenoid, how it is affecting the magnet which is in the other solenoid. A force is acting on this magnet which makes it oscillate, and force is acting on this magnet means there must be a current here. There must be a current in the solenoid which will produce a magnetic field, and that magnetic field will exert force on this magnet. But how is that current produced? That current is produced because of motion of this magnet in this coil. So, if I move the magnet in this coil in and out, a current is produced in the solenoid. Both are connected, so the current is produced here, the same current will go in the other solenoid also. The question is, if I move the magnet here, why should there be a current here? Now my circuit is not moving. In Q V cross B, if I try to utilize, I do not have V. The coils are not moving. This solenoid is not moving. The electrons, free electrons, they are not moving. Of course, random motion is irrelevant, I am not talking of that, but no systematic motion. So, I cannot use V cross B, Q V cross B. How come electrons are being driven in this coil? Now, electrons will experience a force only if either you have electric field or you have magnetic field and the electrons are moving in a systematic way. Since the second option is out, I am somehow producing electric field, and that is the new physics. When I am moving the magnetic field anywhere at any point, the magnetic field is changing as a function of time. If I am just keeping this magnet here, I have magnetic field different at different points but constant in time. But when I am moving the magnetic field at any point changes as a function of time, and this changing magnetic field, that creates electric field, and that electric field drives current in this coil. So, that is the new physics, that changing magnetic field produces electric field, and that electric field drives the current. So, there is an EMF induced. So, you can induce EMF in a circuit either by moving the circuit in a magnetic field or by making this magnetic field change as a function of time. So, let me summarize what you have learnt so far. We started with a circuit, some kind of circuit, could be a solenoid or could be a coil, but finally it is a closed circuit, and you have some kind of a magnetic field. And if I move this circuit in this magnetic field, I see that there is a current. So, if the circuit moves, in a magnetic field, you have a current in this, and what drives the current? The current is driven by F is equal to Q V cross B force, magnetic force. This Q is for the electrons, charge on electrons, free electrons in the circuit. V is the velocity of the circuit that we give, and that is also the velocity the free electrons get, and B is the magnetic field at that particular site. And then over this entire circuit you see how much is this force, and that drives the whole current in the circuit, and we say that an EMF is generated. In battery also you have some chemical reactions. So, they drive the charges and we say that an EMF is generated. Similarly, here the magnetic force drives the current and we say that an EMF is generated, and that EMF is that drives the current. So, an EMF is generated, electromotive force is generated. How much is that EMF, which is measured in voltage? So, there are some rules. It says that first you define a quantity called flux of magnetic field, flux of magnetic field. And what is that? You take this entire area which is bound by this circuit, and then you calculate something like B dot dA. I won't go in details. Essentially it is multiplication of this area and this magnetic field, taking directions into account, some cos theta etc. will come. So, and then you sum over entire thing, we write that as an integral of this. This is flux. So, B into area, and then the EMF which is generated will be given by the total flux change, rate of change of this total flux with a minus sign. I won't go into all these details. The essential part is that this magnetic force drives the current, creates an EMF, and from there you get all these phenomena. On the other hand, the other thing that we did was, you have a circuit and then you have magnetic field, but this magnetic field changes with time. B field changes with time. The circuit is not moving, but the B field is changing with time. If that happens, an electric field is created, and the electric field which is created at these sites, that electric field drives the current. So, when B field changes with time, then E field is created. So, electric field can be created by a charge, and electric field can also be created by a changing magnetic field. This electric field which is created due to changing magnetic field is known as induced electric field. And this is a new physics. This is a contribution of Faraday. This is essence of Faraday's law. And this electric field which is created, that creates a force F is equal to QE, and with that force the current is driven, and from there we can get that current. And once again, how much is the EMF, corresponding EMF? Current is being driven, so there must be some EMF. How much is that EMF related to this E field? E field is related to B field, and not only B field but how it changes with time, it is related to that. So finally it turns out that the same rule applies. A very, very interesting situation. Here totally the mechanism is different, and the EMF which is generated is given by this rule, and here also the EMF is given by the same rule, although the mechanism is very, very different. Now here is another experiment which works on this principle, that changing B field creates E field. So in this apparatus we have a coil which is housed in this box, and that coil is connected to 220 volt AC. So when the current goes through this coil, that current changes in time because of this alternating character 50 hertz AC, and this changing current here creates changing magnetic field, and that changing magnetic field creates electric field, and because of that electric field, in a circuit, in this coil to which this bulb is connected, in this circuit a current is driven, and current is sufficient to glow this bulb. So, just watch. So, I am passing the current by pressing the switch, and you look at this bulb. Okay. So, in this circuit there is no battery or no connection and no extra power is given. It is because of the electric field which is created here, the electrons are driven in this coil, and that makes the bulb glow. If I put this circuit somewhere here, see what happens. The glow is there, but it is less intense. If I put it here, it is much more intense. If I put it here, the intensity is low, and if I put it here, you do not see the glow. So, the current depends on the height from this base. Why? Because the magnetic field becomes weak, so that rate of change of magnetic field, that also goes down, and less EMF is produced. So, now I have another experiment in which both of these things will be used. The circuit will move in a magnetic field, and the magnetic field will also change with time. We will be moving both magnet and the circuit. So, what it is? This is a syringe body, your normal syringe, on which we have wrapped several rounds of this enameled copper wire, and then at the end we have connected these LEDs. Then I have a magnet. And this magnet I can put inside this syringe body. On the other side, the magnet cannot come out, and this side I will close with my thumb, and then I will move it. As I move it, the magnet is moving inside this, and the coil is also moving. So, there are both motions together relative to each other. Of course, they are moving in different ways, and that should produce induced electric field as well as magnetic force Q V cross B, and both should drive the current. To see the LEDs glowing and establishing that there is a current, we will dim all these lights so that you can see it better. So, I am shaking this syringe and inside magnet, and you see how the LEDs are glowing. We normally call this apparatus Damru, because that is how a Damru is played.